Hello, hello everyone. Myself Yogesh. Today I'm gonna present my topic flat slab. Flat slab are nothing but a reinforced concrete slab with or without drop, supported generally without beams by column with or without flated column heads. Flat slab may be of solid slab or may have recessive formed on the soffits, so that the soffit comprises a series of ribs in two directions. The recess may be formed by removal of permanent filter blocks. Types of flat slab. There are four types of flat slab. Flat slab resisting directly on columns. Flat slab with drop panels. Flat slab with column head. Flat slab with column head. Flat slab with drop and column head. These are the four types. In this flat slab, we have some structural advantages. Number one, increases shear strength of the slab, increases negative movement capacity of slab, stiffen the slab, hence reduce deflection. If we will provide column head, column head is a local enlargement of column at the junction on with the slab. In this flat slab, it increases shear strength of the slab, that is punching shear, reduce movement in the slab. Then flat slab with capital drop panels or both. These slabs are very satisfactorily for heavy loads and long span. It can take heavy loads along long span. Although the formwork is more expensive for the flat slab will requires less concrete, which reduces cost than would be required for flat plates with the same load and spans. They are particularly economic for warehouse, for parking and industrial buildings. Similarly, structures where exposed drop panels or capitals are acceptable. Benefits of flat slab: flexible in room layout, partition wall wherever we require, change the size of room, omit false ceiling, saving in building height, lower story height will reduce building weight, approve the cost nearly about 10%, reduction in reduce foundation load. In shorter construction, it can we can do the slab within shorter time. Flat slab design will facilitate the use of big table formwork to increase productivity. Some of the disadvantages of flat slabs are: the main disadvantages of their lack of resistance to the lateral loads due to wind or earthquake. Lateral load resist system such as shear walls are often necessary. When the loads are spans or both become quite large, the slab thickness and the column size required for flat plates or flat slab are of such magnitude that it is more economical to use two-way slab with the beams despite the higher formwork cost. In this flat slab we have three methods. The first one is finite element analysis, and the simplified method or direct design method we can call, and the third one is equivalent frame method. Now we are designing an example with the help of direct design method. In flat slab there are three three panels, that is column strip, middle strip and panel. In column strip means design strip which having a width of 0.25 of length L2 but not greater than 0.25 of L1. On each side of the column center line where L1 is the span in the direction movement are being determined, measured center to center of support, and L2 is the span transverse to the L1, measured center to center of the support. For middle strip means a design strip bonded on each of its opposite side by column strip. Panel. Panel means the part of a slab bounded on each of its four sided by the center line of the column or center line of the adjacent span. We can see the flat slab design is given in page number 53 of IS 456-2000. This is the design I'm gonna take an example. At first we are taking a longer span and a shorter span. This is the longer span, this is the shorter span. For longer span 6 point, we are taking longer span and shorter span. For longer span L1 is 6.6 and L2 is 5.6. That is division into column and middle strip along. In this we are finding out column strip, middle strip. As we know, in column strip 0.25 L2 that gives 1.4 meter, that shouldn't be greater than 0.25 of L1. As middle strip, this is the diagram of longer span and shorter span. In this, the drop when provided shall be rectangular in plan and have a length in each direction is not less than 1/3 of the panel length. The width of the drop at right angle to the non-continuous edge and measured from the center line of the column shall be equal to half the width of the drop for interior panels. Since the panel is large, it is desirable to provide drop. So we are providing drop dimension along longer span and shorter span both. For this longer span drop, it shouldn't be less than L by 3. So we are taken as 2.2 meters. For shorter span it's 1.86 is. So hence we can provide a drop of size 2.2 and this 2.2 meter, that is in column strip width. Column head. When column head are provided, the portion of column head which lies within the largest circular cone or pyramid that has a vertex angle of 90 and can included entirely within the outer line of the column, and the column head shall be considered for design purpose. Column head dimensions for longer span and shorter span. In this column head and shouldn't be larger than L by 4, that is 1.65 for longer span and for shorter span 1.4. Adopting the diameter of column head as 1.30 meter, that is 1300 mm. Depth of flat slab. The thickness of flat slab up to the span 10 meters shall be generally controlled by consideration of span, that is L effective depth Length to effective depth ratio is given below. That is for cantilever 7, simply supported 20 and continuous for 26. For, for flat slab with drop, effective to effective depth ratio given below, given above shall be applied directly, or otherwise the span to effective depth ratio in accordance with above shall be multiplied by 0.9. For this purpose, the longer span of the panel shall be considered. The minimum thickness of the slab shall be 125 mm. So this is a continuous slab, so we are considering a flat slab of continuous slab over a span not exceeding 10 meters, that is L by D equal to 26. So we want effective depth, that is D is equal to L by 26. From this we got effective depth, that is 260 mm for longer span and 220 for shorter span. Taking effective depth of 25 mm is equal to overall depth is equal to this 25 mm is taken as cover, so overall depth is equal to 260 plus 25, that is 285 mm, that is greater than 125 mm, the minimum slab thickness in IS 456. So it is safe to provide the depth of 285 mm. Estimating of load acting on the slab. So dead load acting on the slab is equal to 0.25 into 25, that is 6.25 kilonewton per meter square, that is WD1, and floor finish we are taking as 1.45 kilonewton per meter square, that is WD2. The live load 7.75, so that is W1. So the total dead load WD1 plus WD2, that is 7.7 kilonewton per meter square. The design live load shall not exceed 3 times the design dead load. So we are checking W1 by WD, that is 1.000. It's not increasing greater than 3, so it is okay. The total design load is equal to WD plus W1, that is 15.45 kilonewton per meter square. Right? Now we have to find total design moment for our span. The absolute sum of positive and average and it given by a negative bending moment in each direction shall be taken as MO is equal to WLN by 8. This is given in page number 55 of ISO 456, where MO is the total moment, W is the design load on an area, L1 by L sorry W equal to design load on an area L1 L2, where Ln is the clear span extending from the face to face of column capital of walls, but not less than 0.65 L1, when L1 and L2 are the length of the span. Circular support shall be treated as square support having the same area. If we have the same area, we have to take same as circular support. So equivalent side of the column head having the same area is equal to pi by 4 d square, that we got 1.152 meter square. That clear span along long span is equal to, so we are 6.65 minus half this area minus half this area, so we got 5.448, that is greater than 4.29. Clear span along longer span, so ln is equal to 5.6 half this area minus half 2 times half this area, so we got 4.44 and should not be less than 0.65 L1, so hence okay. For now total design load for longer span we got we have length Ln and L2. For shorter span Ln L2, so we have the formula of W L2 Ln. So we got, for longer span we got the design load as 471.36 kilonewton. For shorter span we got 452.74 kilonewton. For that we have to find absolute sum of negative and positive moment in a panel along longer span as well as shorter span. So Ln and L2, we have the formula of MO equal to W Ln by 8. So we got the moment is equal to 320.99 kilonewton per meter square. For shorter span we got 251.2 kilonewton per meter square. So now negative and positive design moment. Negative and positive design moments is located at the face of rectangular support, circular support being treated as square support having the same area. For interior span, the total design moment MO shall be distributed in the following proportions. That is, negative design moment we will take it as 0.65 and positive design moment we will take it as 0.35. In an end span, the total design moment shall be distributed in following formulas. Interior negative design moment is taken as 0.75, 0.10 divided by 1 plus 1 by alpha c, where alpha c is the ratio of flexural stiffness of the exterior column to the flexural stiffness of the slab at the joint taken in the direction moment at being determined, and that we will find it as alpha c is equal to summation of kc by ks, where Kc is the sum of the flexural stiffness of the column meeting at the point where Ks is equal to flexural stiffness of the slab expressed as movement per unit rotation. And it shall be permissible to modify these design moments by up to 10%. So the long as the total design moment for MO for the panel in the direction considered is not less than required by MO is equal to W Ln by 8. So negative moment section shall be designed to resist the larger of the two interior negative design moment determined for the span framing into the common support, unless an analysis is made to distribute the unbalanced moment in accordance with the stiffness of the adjoint parts. Now column strip. In column strip, negative movement in an interior support. An interior support, the column strip shall be designed to resist 75% of the total negative movement in the panel at the support. For exterior support, the column strip shall be designed to resist total negative movement in the panel at the support. For exterior support, consists of a wall or a column extending for a distance equal to or greater than 3/4 of the value of L2. The length of the span transverse to the direction moment are being determined. The exterior negative moment shall be designed to uniformly distributed across the length L2. For positive movement in column strip, for each span the column strip shall be designed to resist 60% of the total positive movement in the panel. For middle strip, the portion of the design moment not resisted by the column strip shall be assigned in adjacent middle strip, and each middle strip shall be proportioned to resist the sum of the moment assigned to its two half strips, and that middle strip adjacent and parallel to the edge support by a wall shall be proportioned to resist twice the moment assigned to the half the middle strip and corresponding to the first row. For this we have to find stiffness calculation. For that we want height of the flow, that is we are taken as 4 meter, and clear height of the column is equal to height of the flow minus depth of the drop, thickness of the slab minus thickness of the head. So we got the height of clear height of the column as 3275 mm. So the effective length of the column we should multiply with 0.8, that we got 2620 mm, that is middle strip. Assume one hand inch and another hand fixed. And the stiffness coefficient formula we have alpha c is equal to summation of kc by ks. From that we got stiffness coefficient for longer span, we got kc and ks, that is we got stiffness coefficient as 1.39. From page number 56, table 17 of IS 456, there we will got a minimum permissible value of alpha c, imposed load or dead load, and ratio of L2 by L1. From there we will get this value 0.848 and WL by D equal to 1, that is alpha c minimum we got as 0.7. Hence the correction for the pattern of loading in the direction of longer span is not required. Here this is the table. For shorter span we got alpha c as 2.79. From table alpha c minimum we got 0.75. So hence okay, hence the correction of pattern loading in the direction of shorter span is not required. Distribution of bending moment across the panel width. For longer span we have these formulas in page number 55, sorry. For longer span, negative bending moment at exterior support. From this formula we got minus 121.34 kilonewton meter. For positive span bending moment we got 90 kilonewton per meter square. Okay, negative span bending moment at interior support we got minus 166.50 kilonewton per meter. For middle strip we got these values. For shorter span, column strip, middle strip, we have calculated. Effective depth of the slab. Thickness of slab for considering of maximum positive moment, where the slab maximum positive bending moment occurs in column strip. Longer span we are taken as 90.91 kilonewton meter. Factor bending moment, that is 1.5 into 90.91, that is 136.36 kilonewton meter. From these formula, where B is taken as 2800, in annexure G, we will get this formula. We are taken as concrete grade as M20, so we got D is equal to 132.83 mm, that is approximately equal to, we are taken as 140. Using the 12 mm diameter, overall thickness of the slab is 140 plus 15 plus 12 by 2, that is diameter, we got 161, so 170 mm. The depth of the longitudinal direction as 70 minus 15, 12 by 2, that is 150 mm. The depth along longitudinal direction, that is 150 minus 12, 130. So The thickness of the drop for maximum negative moment consideration as the thickness of drop for wherein panel is mu 0.138 FCK BD square. From there we got 254.3 and we had taken as 260 mm. Use 2 mm diameter. So the overall thickness of flat slab is taken as 260 plus 15 plus 12 by 2, that is 281 mm. Here is the diagram of this longer and shorter slab. And the shear in flat slab. For shear in flat slab, the critical section for shear shall be taken as d by 2 from the periphery of the column, or we can say it as drop panel, perpendicular to the plane of the slab where d is the effective depth of the section and the shape in the plan is geometrically similar to the support immediately below the slab. So check for shear developed in the slab. For this in IS 456 page number and 57, from there we will get shear in slabs. So the critical section for shear for slab will be at a distance of d by 2 from the face of drop. So perimeter of the critical section as 4 into 2340. From there yeah, that is 4 into 2340, we got 9340. So the total factored shear force, we have formula, that is 1.5 into slab thickness into L into L2 into 2.34 into 2.34. So we got 729.78 kilonewton nominal shear, that is tau v vu by bd. So we got 720 0.55 Newton per mm square nominal shear, and the shear strength from the formula tau c is equal to 0.25 root of ck, we got 1.11 Newton per mm square. And then permissible shear stress is equal to tau b should not be greater than ks tau c. So this is the modification factors from page number 38 we can find a modification factor for tension reinforcement. If tau c is less than tau c, tau v is less than tau c, then safe design, okay. If tau v is greater than 1.5 tau c, then the slab should be redesigned. So check for shearing drop. This is the formula, b naught is equal to pi d plus d. So we got 4.89 meter, v is equal to 1.5, 15.45. We calculated and we got v is equal to 812.27 kilonewton. So tau v is equal to 812.27 into 10 to the power 3 divided by 4890 into 260. So we got tau v as 0.683 Newton per mm square. That is nominal shear stress. So we will find nominal shear stress for drop, that is tau c is equal to 0.55 root of ck, that is 1.11 Newton per mm square. So tau v is less than tau c, though it is safe in shear. Reinforcement detail. For longer span, negative exterior reinforcement. So we got this formula for annexure G. So we got ASTS 4209. We are using 12 mm dia bars, and the spacing we got as 36 mm center to center, and then positive steel ASTS 3122 mm square, center to center spacing we got 135 mm center to center. For column strip in shorter span, we got AST 3768.9 mm square and clear spacing as 42 mm center to center. For middle strip, we got AST as 1182 mm square, uses 12 mm dia, and we got spacing as 280 mm center to center spacing. This is the design of the flat slab. Thanks for watching this video.